Alright, welcome to Unit 3, Day 4, Operations with Radicals. Now, something that I'm going to emphasize today is that I'm going to be working with radicals. You're going to see me leaving them in radical form. But if you prefer the rational exponents that we worked with yesterday, please go with that you can actually use either. So on this problem, if I was working with it in radical form, I would actually go ahead and say that this is the cube root of 27 times 2, because 27 is 3 cubed, and that's the largest perfect cube that will divide out of 54. I would have y to the 12th, z to the 7th, and so now I would simplify out what I can. The cube root of 27 is 3. I know that the 2 is going to remain inside there. Now I'm going to take care of the y. If I do 12 divided by 3, that's y to the 4th, evenly. 7 divided by 3 is 2 with a remainder of 1. So z to the first inside the radical. There's my answer. Now, yesterday we went over rational exponents. So if you're feeling on this problem, you should set it up as such. 54 to the 1/3, y to the 12 over 3, z to the 7 over 3. You certainly may. What that does is it works out much the same, where the 54 you would write as 27 times 2. The y could go ahead and reduce to a 4. The z will stay to the 7/3. Now on the number, you would actually go ahead and apply the 1/3 power to both 27 and 2. And while I'm at it, I'll write 27 as 3 to the 3rd. And what that does is it arrives at the same answer, z to the 7/3 out there. So 3 to the 3rd to the 1/3 actually cancels to just 3. I'll have a 2 to the 1/3. I have a y to the 4th. And I have a z to the 7/3. Now, if you were to convert it back into radical form, 3 and y to the 4th would be outside. For the z, you would need to consider what the mixed number is of 2 and 7, or of 7/3, which is 2 and 1/3. So z to the second outside, and the 1/3 means that it's going to have a z to the first inside, also with that 2 that was to the 1/3. Now, obviously, I think this was a lot less work with the radicals, so sometimes radicals are less work than with rational exponents. You just kind of got to weigh your options on what you feel more comfortable with. You can tell there's a lot less red on the screen than there is purple. So I'm going to be kind of leaving stuff in radicals for today's class. Alright, I liked this blurb that I found in the textbook about how do you know when you're done simplifying a radical expression. The index n is as small as possible, meaning the power of the root is as small as it can possibly be. Radicand contains no factors that are nth powers of the integer or polynomial. What that means is that there's no perfect squares that you can divide out of the square root. That there's no perfect cubes that you can divide out of a cube root is what that means. The radicand contains no fractions, and the reason why that's so important is because of this last one. That means that you would have an irrational denominator. No radicals appear in the denominator. That's the big two. We'll be talking about those a good bit today and tomorrow. So for this problem, the problem with it is that the last thing is happening, that there's a radical in the denominator. To cancel out that radical in the denominator, I need to make that 3 a perfect square, something I can square root. To do that, I'm going to multiply it by the square root of 3. That will make it the root of 9, which I can work with. Now, if I'm going to do it to the denominator, I must also do it to the numerator. That way, what I'm really multiplying by here is 1. Root 3 over root 3, that's 1. I'm multiplying the number by 1. I'm not changing anything on it. So the numerator is now 2 times the square root of 3, and the denominator is the square root of 9, which is simply 3. Don't think that you can reduce this fraction, root 3 over 3. You cannot, because this is not in a square root. That kind of wraps it up pretty well in this problem. Just realize you cannot have a root in the denominator. Alright, so before you go headlong into doing that process every single time, look and see if there's simplification that can be done. So don't do times the square root of 9 over the square root of 9. Also, right here, the square root of 9 is a perfect square. So you could actually turn that into a 3, reduce your numerator. But I tell you what, since they are both in square roots, you can actually go ahead and divide these two. So I'm going to actually reduce the fraction as the square root of 3. Because square root of 27 divided by square root of 9 is the square root of 3. And as I look at that, there's no perfect squares that can be divided out of it. I'm actually done. Now that was an easy problem. Alright, on this problem, you could go several routes on doing this problem. There's nothing that will reduce between the roots. What I'm going to do is I'm going to go this route. I'm actually going to make 18 a perfect square. I know that 18 can become the square 32 or 36 if I double it, because 36 is a perfect square. Don't go multiplying by root of 18 over root of 18. That'd be a lot more work than what you need to do. So on this problem, all I'm going to do is multiply by the root of 2 over the root of 2. And again, that's because that will make the denominator the root of 36, which I can take the square root of, saving yourself some work. On the numerator, this will become 5 times the square root of 14, the root of 7 times the root of 2. And on the denominator, like I said, it's the root of 36, and that denominator will change to a 6. And still 5 root 14 on the numerator. Look for anything that can divide out right here between the 5 and the 6. If there is, do it. But right here, we're done. 5 root 14 over 6. Alright, while it looks like there's really nothing going on this problem, it's the fact that there's a fraction within the root, and that's where the issue is. Because this would be rewritten as x, the square root of x to the 6th over the square root of y to the 7th. Alright, now what I personally like to do is I like to go ahead and just reduce both of those as much as I can. So on the numerator, that's going to be x to the 3rd power, 6 divided by 2. On the denominator, 7 divided by 2 is going to be 3 with a remainder of 1. So y to the 3rd and a remainder of 1. Don't like that because that's an irrational denominator. Can't have a radical in the denominator. So what I'm going to do is I need to make this square root of y work itself out. I'm going to do that by multiplying by square root of y, top and bottom. So now what I'm going to have is x to the 3rd root y on the numerator. On the denominator, I'll now have y to the 3rd root of y squared. Now the root of y squared will be y to the 1st power. When I put that with y to the 3rd, that'll be y to the 4th power. And I'm going to write that out for you. Again, the square root of y squared is y to the 1st power. When I combine that with y to the 3rd power, I get y to the 4th power. So my final answer, x to the 3rd times the square root of y over y to the 4th power. Alright, here comes the trippy stuff. We got 4 more problems to look at, folks. Basically, whenever you've got multiplication, you can multiply the coefficients, what's in front of the root, together, and you can multiply the roots together if they are the same power root. Both of these are a square root, so you can. Let's go ahead and get rolling on it. That 6 times 4 will be 24, times the square root of 8 times 2 is 16. C to the 3rd times C to the 1st is C to the 4th power, and D to the 5th times D to the 3rd is D to the 8th power. Now I'm going to simplify the root as much as possible, and this one actually completely simplifies. So I've got 24 times the square root of 16 is 4. The square root of C to the 4th is C to the 2nd. The square root of D to the 8th is D to the 4th. Remember, I'm dividing by 2 on these exponents is how I'm getting these. And the last thing I need to do is just 24 times 4, and that's 96. C squared D to the 4th. And that is your final answer here. Alright, lastly today, on these last 2 examples, we're talking addition and subtraction and when that can, in fact, happen. Right now, I cannot add these 2 roots together, so I'm actually going to work on just simplifying them independently. Looking at that root of 8, the 4 root 8, I know that the largest perfect square that will go into 8 is 4. It goes into it twice. Plus 3 root 50. While I'm at it, I might as well talk about 50. 25 will go into 50 twice as well. Alright, so now let's simplify those independently. Over here on the left, I can take the square root of 4 is 2. So it's going to be 4 times 2 times the square root of 2. Plus, over here on the right, I can take the square root of 25. That's 5. 3 times 5, square root of 2. And now I'm just going to write this as 8 times the square root of 2 plus 15 times the square root of 2. Nothing mind-blowing up to here. This last step also is not mind-blowing. Think of these as like terms. That root 2 has been distributed to the 8 and the 15. So I undistributed it there. I kind of factored it out. Yeah, this is all related. I factored out that root 2. And what is 8 plus 15? It's 23. So 23 root 2. You usually hardly ever see anybody show this step right here in their notes. They go straight from 8 root 2 plus 15 root 2 to 23 root 2. Now, if this is the root of 2 and this was the root of any other number, you can't do that step. You just have to leave it as addition and you couldn't combine them. The only way you can combine them is if it's the same power on the root on both of them and it's the root of the same thing. Alright. By the way, that 2 is called a radicand. I should probably use that term. So the radicands matched. Alright, wrapping up with one last problem here and we'll be done on this lesson. We're still dealing with square roots here, so let's take out the largest perfect squares on each of them. So for the first one, the 5 root 4 goes into 12 3 times, 4 being the biggest perfect square, plus the largest perfect square that goes into 27 is 9, goes into it 3 times, minus, let's do a little bit of work to figure out the largest perfect square that goes into 128. Alright, the largest perfect square that goes into 128 is 64 goes into it twice. Now, hopefully you were able to figure that out for yourself. Now let's simplify each of these by taking the roots that we can. So the root of 4 is 2. So I've got 5 times 2 times the root of 3, plus, right here I've got the square root of 9 is 3, so 2 times 3 times the square root of 3, minus, the square root of 64 is 8, so 8 times the square root of 2. Simplifying this down now to 10 root 3 plus 6 root 3 minus 8 root 2. And as I look at this, there is more simplification that can happen, and it's happening from right here on these first two terms. They can be combined. I cannot combine them with the last one because it's the root of 2. So 10 root 3 plus 6 root 3 is 16 root 3 minus 8 root 2, and I am finished. Good job today. We'll pick up some more simplification of radicals likely tomorrow and keep on working through this unit. It's becoming quite the long one.